So, welcome to this webinar about forced and natural convection in CFD analysis. So this will be the topic of today's webinar. And we have a lot of interesting things to talk about, and I hope you will enjoy today's topic. And if at any time you have some questions during the webinar, please ask, and I will try to answer in live or maybe at the end of the webinar. So this is the topics we'll talk about today. First of all, a short introduction about the CFD. Then I'll do a quick reminder about thermal analysis. I talk about the difference between structural and CFD thermal analysis. And after that comes the most interesting parts, the forced convection simulation and the natural convection simulation. So today's webinar will be very training focused, so I'll try to show you exactly how to perform forced convection in Midas NFX. So first of all, Midas NFX is a general CFD software, so we have a range of applications and that you can perform, so heating device, electric and electronic device, plants, fluid machinery, automotive, marine and offshore, construction, and aeronautics. So NFX has some solutions for all these areas, and today we will investigate more in details the heating device and the electric and electronic device area because of the thermal CFD, and I'll give you some concrete example a bit later. So, Midas NFX CFD is a complete platform with NFX GUI and a CFD solver. So you have the pre-post, the solver, and the post-processor. And the good thing is that the post-processor and the pre-post are the same than the structural interface. So if you already have Midas NFX structural, it will be very easy to get with the interface, which is anyway very intuitive. Moreover, the capacity for CFD, so NFX includes 5 modules for CFD: general fluid flow, fluid and heat transfer, so it will be the topic of today, species concentration analysis, then we have multi-phase flow, and we can use mesh deformation as well. We have 14 turbulent models to really model the turbulence. We have proved accuracy and stability, so a lot of benchmarks to be sure that the results you get are the correct results. And we have now parallel computing with the GPU, which is a new feature of NFX 2014 R2. So to compute big models, it will be much faster. And the thing you should know also is that NFX is a software which is evolving very fastly. So every year and every 6 months we'll add some new features, so you'll have a more efficient solution. Now let's go to the second part, which is the quick reminder about the thermal analysis. Okay, so this is the basics about heat transfer analysis. First of all, so I talked about it in last week's webinar, but as today's webinar is also focused on heat transfer, I just added 2 or 3 slides to remind you about these basic principles, because it's very important for today's webinar as well. So to analyze a heat flow due to the temperature, so you have different types of heat transfer methods: convection, conduction, and radiation. So conduction is the heat energy transferred through the vibration of the molecules. So in fact, you cannot really see it, but when you have 2 solids, one with another, you have some interface between the 2 solids, and the vibration of the molecule makes that the temperature can be transferred. So the rate of transfer, it depends on the property of the material, of course, and this is the conduction coefficient. Now the convection is the energy transferred through the movement of a medium. So generally a liquid, but it can be a gas also then, like the air, for example. And the radiation is heat energy transferred through electromagnetic waves. So if I resume these 3 points, you have the basic equations here. So the conduction, so as I told you, the heat energy transfers through the chain vibration of molecules. So the basic equation is the Fourier equations. So the gradient K delta T. K is the conductivity of the material. Then you have the convection. So convection is generally defined by such relation. So H is the convection coefficient, A is the surface on which you have the heat transfer, T is the external temperature, and T, which depend on the time, is the temperature which is calculated through this equation on the surface. And then the radiation is a bit more complex because it's a nonlinear kind of relation. So you have Stefan Boltzmann constant, and the temperature is at the power 4. Now in convection you have 2 types of convection, and it's the topic of today's webinar. First of all, you have natural convection, so the cooling due to the air, and you have also forced convection, the cooling due to a fan, for example. So I'll explain the difference right after. Now let's talk a bit about difference between structural thermal simulation and CFD thermal simulation. Maybe some people may not do the difference between the two, so they're wondering maybe why I'm talking about structural thermal simulation and CFD thermal simulation. Well, the reason is that the modeling is not the same. When you are doing structural heat transfer analysis, what you're doing is that you're only considering the solid parts in your model. So you have the solid volume, you are applying the heat transfer condition, and on the area which is around the part, you just apply a convection equation, which is defined by the equation I just showed a few slides before. So in these conditions, one of the major hypotheses is that the fluid is at ambient temperature, which is constant. So you have, let's say, always 25 degrees around your part, and this is something that is more or less constant. So you don't know actually what is doing the fluid around, but you're just considering it like a boundary condition. And then you have CFD, fluid-solid coupled analysis. So in this type of analysis, you are modeling the solid as well as the fluid volume. So in this type of analysis, you are modeling everything, and you don't need to add this convection condition between the solid and the fluid, because this will be calculated automatically by the software. So if I give you an example of structural heat transfer, you can take this example from last week's webinar, the board analysis. And this is the example we'll see today, which is the cooling due to the fluid. So when you have, so this is the forced convection. I'll talk about it a bit after. Now, when should I use structural heat transfer, and when should I use CFD heat transfer? So first of all, structural heat transfer is used when the fluid temperature can be assimilated as uniform around the solid part. And when we investigate the behavior of the structural components only under heating, so like convection, heat generation, and radiation, or when we investigate the stress and the deformation caused to the parts due to the heat load. So in these conditions you can use the structural heat transfer. Now CFD heat transfer coupled analysis is used when the distribution of the fluid around the object need to be studied. So you don't know what will do the fluid, and maybe it will be highly not uniform, so you cannot just assimilate it as a boundary condition. So it is to investigate the impact of the object on the environment, or to investigate natural or forced cooling. So I'll talk about that now. Now let's talk about forced convection simulation. So first of all, what is the forced convection? Well, this is the kind of movement of the heat inside your model, which is created by a fan, a wind, or maybe a coolant. So the movement of the temperature is kind of forced by the movement of the fluid. So this is why it's called a forced convection. So the movement of the fluid is non-uniform and very related to the movement of the fluid. So you have a simple example, which is a cooling of some electronic board, and here you have a fan. So the fan will be available in NFX 2014 R2. So I'll do this example today, and what you will see is that the fluid, which is here, so this is the velocity distribution of the fluid, you see it goes from the inlet to the outlet, is causing the change in the temperature on the structural parts. Now these are a few examples of application. So this is mainly electronic application, like I talked about, because this is very used in electronic equipment. So these are all analyses done by NFX. So you can do this analysis on the board to view the cooling due to the fluid, and then you can, let's say, extract the temperature and apply it on your structural model in order to view the deformation of your board, for example. Now there's something also very important. I will not detail it today, which is the simplification of the model, because when you have generally such electronic equipment, the CAD model that you received may be very complex, and of course you cannot just simulate it like that, so you have to simplify a lot before you can do something. So what you should remember is that simulation is like a virtual test. So what you need to think about is what is the situation actually being modeled, and how does it relate to the usage scenarios that I am considering. Now what you need to know are the inlets and the outlets of the device that you are testing, and for the flow, but also for the heat, because the two are coupled together, and the boundary conditions. So where are the conditions that I know in this model, what is specified in my test my test benchmark, and what will be condition of the flow speed, the pressure, the temperature, and the heat dissipation. So this is determining the boundary condition is not easy. So this is why what you can do to think about that, how to define this boundary condition, you can think about these four questions. What do you know about the test conditions first? Which variables are controlled in my system? What are the unknown that I'm trying to measure? So what do I want to get? And what are you trying to determine? What is the goal of your simulation? Now you have three things that are to be thought about to determine all the boundary conditions for the flow and for the heat. So the first one is the driver. So what will cause the heat to flow? What will cause the flow to flow? So what causes the air to flow? Where are the fans? So maybe you have internal fans. Where is the pressure upstream? Or maybe do you have a suction downstream, what is the supply flow rate, and about the heat, what is generating the heat in my model, what are the thermal paths through the model. Now for the inlets, you have to think about, do I have a stagnation inlet, so inlet which is fixed, a velocity inlet, a mass flow inlet, and for the heat, what is the ambient temperature, what is the heat generation, volumetric or surfacic, and for the outlets, what is the pressure outlet, negative velocity or mass flow, and same ambient temperature, convection on exterior surfaces. So now we will begin the big part of today's webinar, which is the forced convection flow analysis in Midas NFX. So I will show you the full process, how to perform such analysis. So here you have a view of the system that I will consider. So this is you have a small PCB with 2 chips. You have a larger chip with a heat sink in aluminium, and you have a capacitor which is also in aluminium. So the ambient air is at 25 degrees Celsius. The capacitor is at 38 degrees Celsius, and you have a heat source on this large chip. So maybe this is the processor inside my system. So this is the value of the heat source. And then the aluminum case, so the outlet will be here and the inlet will be here. So on the inlet I have a velocity of 4 meters per second and 25 degrees Celsius as the temperature inlet boundary condition. Okay, let's go on. So now I just opened Midas NFX, so you should be able to view the software right now. Okay, so what I'll do is that I will start a new project. So I'll choose Matter, and I will just import my model. So this is my my model. So you see that there's a case, there's a board inside with 2 chips, and the large chip, the heat sink, and the capacitor. So the round one represents the fan, so this is the inlet, and the other, this is the outlet. So let's begin. So the first thing I have to do is to create the fluid volume, because you see there's no fluid right now. So I just hide all the guiders so you see a bit more how it goes. So first of all, to create the fluid volume, I have to create a surface at the inlet and the outlet to be able to separate the flow going in and the flow going out. Then there's a lot of things to consider, which is also very important. This is my part should be imprinted one on another. So to be sure this is the case here, what I can do is that I can check the shape, check the duplicates, and if I click here, you will be able to view in the model what are the surfaces which are effectively duplicated. So this is very important in order to mesh correctly my model and to get the accurate results. Otherwise, if you don't have this, you could also assign contacts, but this is better to just merge the nodes together. So the surface which are like that means you already have some shared phase, but you see this surface is not shared, and this one either, this one is not with the case. So to do that, I simply use the auto connection tool. I select all my parts and I click on OK. And now if I check the shape again, you see that now it's okay. So this face that was not shared is now shared, this one too, and this one too. So I can go on. Now that I've done that, I can create the fluid volume. So let's make the CFD volume extraction, select the parts, select the inlet and the outlet, and I have to be sure that the volume I define is large enough to contain my model, so I can use the preview, and it seems to be okay, so I just created. Okay, I did something bad. I deleted the case. I deleted the structural part, so I will come back. This is a good thing because you can always come back if you did something which is not what you wanted. So I click here and here. So here I assign right dimension, and here I have to uncheck this option, delete target, otherwise it will delete the structural parts in my model. Now it's okay. Okay, what I'll do is I just delete the external fluid that I will not consider in this analysis. And if you go in the walk tree, so let's show only the internal fluid volume, which is here, and that will be my main analysis target. So I'll give it a name again. I'll change the name to fluid. Okay, so you have to press F2 to change the names. Okay, and now I'm ready to, my model is ready, so I can begin to assign boundary conditions and the materials and everything. So first thing is to create the materials. So let's create a fluid material, air. So let's use the air at 25 degrees. Okay. And let's create the solid material as well. So solid, let's use aluminium. Okay. And for the other parts, I don't want to create it right now, so I will just import it from the previous model that I created before. So I don't need the air because I already have it. Okay, so I have now, so this first alloy steel, I don't need it, this is a structural material. So I have air, aluminium, larger chip, small chip, and PCB. So these materials are all different. And if I open this, you see that the heat source value is defined here. So this is the heat source. Small chip, you have same the heat source here. Let me check. I think just one thing. Okay, it seems like the heat source is not correct, so I just changed that. So my heat source for the small chip was 6.56. Small chip. Oh no, I'm just telling bullshit. This is correct. Okay, this is the correct value. Sorry about that. Okay. Now let's create some properties which are going with this material. So to create CFD property, air, aluminium. So these properties will be assigned to the mesh sets in order to transfer the material property to the mesh. Small chips, and PCB. Okay, I created my materials. Now that I've done that, I can assign the boundary condition on my model. So first thing is I make it transparent, so it's better to display mode line only. Okay, so you see the inner of the model, and I just assign a boundary condition. So first of all, the flow inlet. So let's assign the inlet. So it's 4 meters per second. Now let's assign the outlet condition. So 0 pressure. Let's assign the wall conditions. So I select all the face except the inlet and the outlet. So all the faces of the solid, of the fluid which are in contact with the solid need a wall condition. If you don't assign it, it will not work. So I'll use a wall distance applied, and the value is 0.000333. So I'm not detailing why. You can find that in the tutorial. And now I assign the boundary condition for the flow, and now I have to assign the boundary condition for the heat. So temperature of the inlet is fixed at 25 degrees Celsius. Now what you have is that what I'm doing is that I'm not considering the external flow to this. So what I'll do is that I replace it by the heat flux. So in this case it's possible to use also heat flux in CFD. So here I choose manually the surface because I don't want to assign it to the parts which are inside, only to the surface external in contact with the case. Okay, so it makes 14 surfaces, and I have to define the value for the heat flux and the reactive heat flux. So also how to define these values, this is explained in the PDF tutorial that I'll tell you at the end of the webinar where you can download that. Okay, and you have to fix also the temperature on the condenser. 1, 2, 3, and 4, and 5. 38 degrees Celsius. Okay. So now all my boundary conditions are defined. So what I have to do is mesh the model. So I'll hide the label so I see a bit better to mesh. And what I'll do is that I will apply size control on the parts inside. So it will be smaller because I need more accuracy on these parts. So 0.002. Okay. Great. And let's mesh it with 3D mesh. So I have to use the air property. Let's look at the advanced options. So if your high order element is activated, unactivate it, because it's better to not use it for CFD. Okay, I select this. I can give it a name if I want, but I don't need here. Okay, apply. Okay, so this is my fluid volume. If I want, I can check if the mesh around these parts is smaller. I don't really need, but if I want, I can use the ISO surface, for example, like that. So you can move it directly to view the mesh around, and you see there's a nice gradation between this part and the external mesh. So this is what I wanted to get. Now I have to mesh the internal parts. So what I will do is that I will merge the nodes of this internal part with the node of the fluid in order to be sure to have the transfer of thermal transfer of heat between these two parts. So I'll show you how to do that. So first of all, let's hide the mesh and show the solid. Let's hide the fluid and the case, and I can mesh these parts. So click on 3D, and here it's very important, don't forget to merge the nodes together. So you have to check this merge node option, and there's another option which is match the adjacent faces. So this is very important too, because it will match exactly the mesh from the fluid which is around the parts. So you have to check that. So I just click on my part. Okay, I have to select the right property. So here it's aluminium, apply. So the mesh size will be automatically set to the right one. So this part is larger chip. The condenser is in aluminum. Then let's mesh these two chips with small chips property, and finally the PCB. And now there's the one part that I didn't mesh, which is the external case, which is in aluminum. Okay. So if you didn't assign the right property to a part, you don't need to delete it. You can go into the Mesh tab, Element, Parameter, then you click on the tab 3D and Change Property. Then you select the mesh set that you want to change the property, and you select the other property you want to assign. So you don't need to delete the mesh set to assign it again or to remesh it. You can do it directly like that. Okay, so now I have my model that I can use for the analysis. So the following part is how I assign the analysis conditions. So I will create the analysis case. So before doing that, let's think about what I want, because this is the questions I just told you. What do I want to get in this analysis? So I'm interested by the temperature. How the temperature will evolve with the time in my small chips. So this is what I want to get, and I want to be sure that the cooling effect will keep a steady temperature on the small chips. So what I understand by answering this question is that I need to do a transient analysis, because it is depending on the time. So I will create a CFD, transient analysis. So I give it a name, transient, let's say transient 1. And now I have to define the analysis control options. So now I am analyzing the fluid flow, the fluid heat, the solid heat transfer. Now the time increment need to be small enough, because in transient analysis, to solve the fluid, you need to have a very small time increment. Let's use 1000 time steps, and let's use 10 steps for the output of the results. Now I will use turbulent models, this one, and for the field definition I have to define the eddy kinetic energy. So again, if you don't know how to define that, you can there's how to define it. It's written in the PDF tutorial that you can get on the website. 25 and 25 degree. So these are the conditions for this analysis. So I click on OK, and I generate this case. So the only thing I need is to launch the analysis and to wait and to get the result. So now let's think a bit about something, because I want to give you some very important trick today to perform this analysis very, very fastly and get the results you want in 20 minutes. So this is my goal. If you do like that, like we did, so transient with so small time step, so it will take a lot of time. Why? Because let's say if I reach the steady state after 500 seconds, you have to multiply the number of steps by this time increment to get the total analysis time, so it will take a lot of time. And why do I have a time step so small? Because I am in transient analysis, and the fluid flow in transient state requires a very small time increment. So this is, I cannot escape that. But the temperature, on the contrary, doesn't need a so small time increment. So I could put 1 second for if I was only analyzing the temperature. But there's a problem here. If I set it to 1 second, it will not converge because of the fluid. So I have to find a solution for that in order to solve this analysis in 2 steps. So this is what I'll show you. So there's a trick. The trick is the following. So I create first a steady state CFD analysis. And in this steady state CFD, I will investigate only the fluid flow without the heat. So I want to know what is the fluid distribution at the steady state. So this is a steady state analysis, so I don't need a small time increment. I can use 1 second. I'll use 1000 time steps, and let's see which other condition I need to define. So same the eddy kinetic energy and eddy length scale. So this is 3192. Okay. The turbulence model. Okay. Now what I'll do is that I will put monitoring on this output phase to be sure to view when it will converge, so to monitor the velocity at the outlet. Let's run this analysis. So okay, let's give it a name. So I will first compute the fluid flow, and then what I will do is that I will take the value I get from this steady state analysis for the fluid, and I will input it in the transient analysis, on which I will do only thermal analysis. So this is the trick. This is called a two-step analysis. So so you have the convergence graph. So you have two values, the velocity and the pressure, and when it reaches a value inferior to 0.001, I have the convergence. So I have to wait a bit that it converges at least. Then you can, this is the value I am monitoring, so I am monitoring the velocity at the outlet. So here I have the value, and I know exactly when I need to stop this steady state analysis when this velocity reaches a steady state. So when it is stable. So now you see here it's converging. So I get already the convergence because these two values are below the CFD norm, which is 0.001. And here in the text window it's written converge. So it gives you the value of the norm which is calculated, the number of increments it did to reach this value. Okay. Okay, I will not continue. It takes approximately 10 minutes. So I'll stop here. And what I'll do, so if I show you what I get, so this is, I get the value of this, fluid. So I get the value of the fluid inside. So I didn't reach a steady state, so for the moment distribution is not really what I should get on the steady state. And same, I can see the pressure, but I don't know yet the temperature. So the trick is I create now another transient CFD analysis. Sorry, I create another transient CFD analysis, and so in this time I don't do the fluid flow, I do only heat analysis. So as I only do that, I can use a 1 second time increment and 1000 time steps. Let's use 10 for the maximum iteration to be sure to have accurate results, and I will get the value of the fluid at the steady state by using the restart file condition. So I click here and I just choose the restart file from my previous analysis. So here you have it. Now for the field definition, 25 and 25. Okay. Click on OK. Click on OK, and now, oh yeah, Now what I will also monitor the temperature on some parts. So let's hide the case and feed volume and also this. So I have these two small chips and the big chip, and I'll use the monitor option to monitor the temperature when I sort this on these three chips. And now I can run this analysis. So let's wait a bit. I hope you're not sleeping. Okay, I didn't choose the right restart file, I'm sorry. Transient and steady, okay. This one. So if you have questions, don't hesitate to ask during the session. Okay, now you see you have only the CFD norm graph, which is already converging, so this is going very fast, and this is the reason why I'm separating this analysis into two analyses. So I'm doing a steady state flow analysis, and I am coupling it with the transient CFD, but only for the thermal. So now I can look at the result on the temperature. So you see this is the result on the chip, and it's converging fastly. So this one a bit less fastly. Velocity, okay. Okay, now let's stop that and I'll show you the final results. So I'll just open another model to show you the final results, because I don't want to make you wait 10 minutes. Okay, let's show all the mesh sets. So first of all, the results of the temperature are the following. So I can use again this cutting plate. So you see you have some heat around the chips. The maximum temperature is around 114 degrees Celsius. So let's make a cutting plane like that, and let's make another one like that. Let's okay, and now you view a bit what is going inside on temperature side. Maximum, so maximum is around here. Okay, and of course, so this is what I wanted to get, and it takes around 20 minutes for the two analyses together. Okay, let's go back to the presentation. Okay, this was because when you make the full simulation, the temperature is converging like that, so you see that you reach the steady state after around, let's say, 500 seconds, so you can say you have around the steady state here. So you don't need to make analysis of thousands increments, you can do 500. Now about the second part, the natural convection simulation. So natural convection is a bit different of the forced convection, because it's I'm not forcing the temperature to go out of my model, but this is the natural process. My model is emitting some heat, and then I want to study what is the impact of this heat generation on the surrounding air volume. So this is a simplified LED model. So you see the chip here generates some heat around, and this is the flow which is up upstream of this LED, which is caused by this natural convection. So in natural convection, you don't need to apply any fan or anything. This is only the density, the thermal, the heat transfer, actually the heat generation, is causing some dilatation of the water around the model, which is causing some movement of the fluid. So you have a few examples of application, and this type of analysis is mainly done also for electronic equipment, like the natural cooling of the PCB board, but it can be done also for the temperature distribution of solid parts around the LED model, for example. So these are two domains of application of this natural convection. And we have a tutorial which is available, so I will not do this tutorial today. It will take too much time, and it's already 6:50. And so if you are interested to get this model, you can go on NFX website and download it, and you can try by yourself how to do such analysis. And if you have some problems, you can send me an email and I will help you. So by the way, I will write my email for those who don't have it. It's sarpin@it.com. So you can send me an email if you want to know a bit more about that. Now, how you can get more training material. So you can go on NFX website. So you have a Learn and Support section in which you'll find the tutorials. So these are basic tutorial about CFD, but we have also the tutorial I did today. So you will be able to download the model with the PDF to test by yourself. And you can also view the next webinar sessions that we'll have in the webinar schedule. So we'll have another webinar on Thursday by Apul Sharma, which will be for designers to explain them the benefits of the simulation. And you're invited if you're interested about this topic. Now, if you don't have Midas NFX, you can download the trial on her website. So 30 days trial, fully functional with all the options. So thank you very much for attending this webinar session, and then I hope you'll join the next webinar, and you can also join us on the social network if you are interested. Okay, now we'll have a small question and answer session. So if you have some questions, please ask right now, and I will answer them in live.